Our next scheduled presentation is by Bill Hanna, and Bill's been doing some work on autonomous mobile observatories. The idea that you can plop a telescope down and it'll behave itself.
Yes. Very good. So, as Roger alluded to, you might say the ideal system is something that you could just drive along the highway at speed and chuck one out the window every 50 meters, and it would just kind of do its own thing. That would be way too hard, I think. So,
The airbag technology is there.
yes, oh yes. Mm-hmm. Exactly. So when I retired about a year ago and moved to Montana, uh, the one thing I didn't plan on, because when we bought the house, we hadn't been, or I hadn't been as active in this at the time, so I didn't check the weather, and basically I moved from a place in Australia where I had about a 25% clouded out rate to a place where I have a 95% clouded out rate. So what I've decided to do is use my skills. I'm a mechanical engineer by design or by education to do some tools and techniques that might assist the group. So next slide, please. Okay. So as we all know, and we certainly got reinforced last night, when you do when you go out in the field, and if you're going to do a pre-point, that just takes a finite amount of time. In certain cases, that time limits you to how many stations you can set up, especially if you're doing a star pre-point. Now, some people, I know John Broughton, David Dunham have worked on this sort of, they put a brick-like pad down and they can pre-point. But this requires you going out, in effect, multiple times to the same site, which under certain circumstances is probably no big deal. Other places it might be. Next slide, please. Okay, so my concept is to have a single thing. I know a lot of people have worked on putting all the electronics and bits in a box and integrating it, but my plan is one object, and I don't know, the form will follow function. What it will actually look like is to be determined based on some of the studies I've been doing, so that you would literally take this thing out, stick it on the ground, and with an initial course alignment that I'll go into, you kind of get it kind of sort of pointed in the pre-point direction, and then it takes off and autonomously does what it has to do. Ideally, for extremely long observations, we might want to be able to track as well. And the big problem is I did a lot of research on the sort of things you could go out and buy. Absolutely everything I'm talking about here is available commercially for thousands of dollars. I mean, beautiful, beautiful, beautiful equipment, but way too expensive. So well, for example, for a commercial mount like the Celestron Star Sense, that thing works really well. But you have to have a CGE Pro mount and, you know, lots of money. So my plan is inexpensive, and we can argue what that means. But I wanted something that could more or less align itself in the sense of pointing the optical axis of the telescope at the pre-point target autonomously. Next slide, please. Okay, so I envision basically everything being in there because, and I'll point this out again later, I will assert that you will be able to set these things up and do your initial course alignment in the daytime. So the system might even have solar cells to trickle charge up the batteries if required. And then sort of the other features you might, depending where you live, and certainly where I live, you might want to put some dew suppression heaters in. you might want it to be able to protect itself by, if it detects certain weather conditions, it chucks a hood over or whatever. And then, of course, you're putting an expensive piece of equipment out in the field, so you might want to have some sort of security-based. Oops. The mouse on the. Well, with it. Oh, this mouse? Want me to wiggle?
Which one is plugged into the projector? This one is here. So it must be coming to it now. I'm not sure what happened. Oh, we have our, what is the magic day show?
We timed that.
The system here has a timeout on it.
Oh, that one.
Unfortunately. Perhaps this can only be so long, apparently.
I see. Yeah.
Computers get
Yeah. So in the ideal, all of this stuff would be in a single thing that you just take out and stick on the ground and do the alignment on. So next slide, please. Okay, as I say, you can go out and spend thousands of dollars and get everything I'm going to talk about, but it turns out there are cheaper versions of these things, and if you go to places like robotshop.com or Sparkfront Electronics, things like that, you can get all the bits to move mirrors and cameras and things around. So all the parts are there, and then obviously something like this is going to have some sort of executive computer that's driving the positioning equipment, starting and stopping the recorder, adjusting the focus perhaps. A lot of people are interested in the Raspberry Pi these days. I do have one of those. Arduino, Micromite, which is an Australian thing from Silicon Chip Electronics in Australia. And then there's various single board computers that can be Linux or Windows based. So there's a lot of stuff out there to choose from. Next slide, please. And so you look at a cult watcher and it says this thing is 28 degrees at 087 degrees. So the idea will be you will go out and set this thing up to point the default optical axis of the device to that place relative to your ground location. So sort of the three axes that you'll have to work with aren't exactly orthogonal, but you'll have a level, an elevation, and an azimuth. And the idea is you go out and pre-point early. You may not know where 087 degrees is, but if you know where the sun is, or you know where the moon is, or if it is nighttime, you know where a bright star is, or in the daytime, if you know where a mountain peak or a transmission tower or a building or whatever, you should be able to say, and the ideal thing would be the device would tell you, okay, it has the GPS, this is where you are, this is what time it is, this is where you want to be, this is where the sun is, turn the thing to this angle, and therefore you'll be pointing at the right place. I played around with this, and I believe you'd have absolutely no trouble getting within 5 degrees of the target, and with a little work you can easily get within 2, which is to say that the optical axis steering assembly only has to make a relatively small correction, certainly no more than 10 degrees, probably quite a bit less. Next slide, please. Okay, and as an old engineering teacher told me, your job's to get the right answer, not to care how you do it much. So if you can get somebody else to do the work for you, that's great. So the azimuth of the sun, azimuth of the moon, you can get from the U.S. Naval Observatory based on your site. You have star catalogs in C2A as your plug-in to Occult Watcher or whatever. When you plan your setup, you look at Google Earth and say, well, is there a transmission tower, for example, or a mountain peak? What this means is you'll have to do a lot of work up front for a given observation to collect all this information, download it into your multiple stations' executive computers, which will then share it and then use the information as appropriate to their specific location. Next slide, please. Okay, so there's a number of ways to steer the optical axis. And the one I'll show now is that I've done so far, a pan tilt where you move in an basically in an azimuth axis and a tilt with a mirror servos, or is something similar to, say, the surveyor camera for the lunar things. Is a worm gear driven thing. Alternate is an XY mirror control. We have two separate mirrors on galvanometers, and they move appropriately to steer the axis, very much like a laser scanner. And then something that I'm especially interested in after my disaster last night is imagine if you had a tripod that could change the length of its legs, and just as there are rotational servos, there are linear servos that fundamentally, at least from a design standpoint, programming standpoint, work the same way. Next slide. Okay, so the first thing I've done so far is I said I will go for the cheapest option, which are just bog standard servos that you can buy at any remote controlled, for aircraft or little buggy-like things that go on the ground. So I went to robotshop.com, and there's this fantastic servo controller board which accepts ASCII commands, which can be produced by anything, really. And it, based on the ASCII commands, it puts out the appropriate pulse width train to control the servo. And for those of you who aren't familiar with servos, a typical servo, and there's no such thing as a typical servo, but a typical servo will have a 180-degree rotation based on a pulse width change from 0.5 millisecond to 2.5 milliseconds that are repeated every perhaps 50 milliseconds or so. Again, there's a lot of standards. No one conforms to them for the most part. And so I purchased a pan tilt system with high-tech, very common, again, these are bog standard servos. A lot of stuff when you're buying a servo, you're looking at the speed that it'll turn and how much torque it'll produce. If you're just moving a mirror assembly, those are immaterial, completely immaterial. But what you do want is a small controlling bit deadband so that you can do fine pointing with the thing. Next slide, please. Okay, so I built a test rig, which I'll show here. So I took a 80 millimeter short tube telescope, used a first surface mirror from Edmunds Scientific, and turns out small mirrors are cheap. The price goes way up as you get bigger mirrors, which might be an issue. And then the optics was pretty much just a standard setup, and I had my laptop controlling the controller board using TerraTerm, which is a free source version of hyperterminal, which is no longer part of Windows for some reason. So what it means is, again, for a typical servo, a change in pulse width of 2 milliseconds, 2000 microseconds, is a 180-degree rotation, or a single microsecond change in width, which is the minimum commandable change from this board, would give this servo a 5 and a bit arc minute change. So, next slide. Okay, so again, I put this thing together. So short tube assembly. I have, next slide will show this bigger, and then there's a pan tilt mechanism with a first surface mirror up here. So next slide. And so again, you can see there's a servo here, and I can have a pan axis and then a servo here with a tilt axis. And of course, the pan axis, one count is one, well, I'll say it differently. On the tilt axis, you get twice as much bang for your buck, because you're with in effect a 90-degree change. As you're tilting the mirror, a single count gives you twice the angular change as this change on the pan axis. And I then shot this down the longest leg inside my house. Next slide, please. And for this particular setup, you know, I just put a ruler up on the other wall. A single count, or a single microsecond change, would represent about this much, or 30 arc minutes, or the diameter of the moon, if you will, would represent this much of a change. Again, you could obviously change your optics and make this anything, but for this particular test, that's what I did. And next slide. And for a repeatability accuracy target, I basically arbitrarily said the width of the moon, 30 arc minutes. Can I reliably get this thing within the diameter of the moon? And what I found, and this is, again, I mentioned the deadband issue. If I make large slews, which is to say, if I slew away from the desired target and then back to it, I can get within a few, maybe not quite 20 arc seconds, or arc minutes, pardon me, repeatability. And that's simply because your bog standard servo does not have a small deadband, which is to say, if I'm, say, making a 850 microsecond pulse width, if I then command it to 851, absolutely nothing happens. I might have to go to 856, 857 for the servo to respond to it. I kind of knew this would happen. I wanted to verify. So basically it proved what I kind of thought I knew, but to keep the cost down, I wanted to see if it was just possible. The one thing that is good news is with a rotational servo, the servo will or can be moved once you remove power from it. And you wouldn't want to sit there and power these things for the hours that you might have to wait. So you'd want to get it positioned and then leave it. And because the mirror simply has so low a mass, although it theoretically could move, my tests show that it will not. So for this particular setup, my assessment is it's good, but it's not good enough. So next slide, please. So the next thing I'll be trying is a so-called digital servo, which I think is kind of a weird name, because all that really is an analog servo with a digital kind of front end on it. It receives exactly the same sort of pulse width, but the digital part examines that and then kind of, for lack of a better word, amplifies the effect So you do get more torque, you get better holding power, it can move faster. The the thing about them is they do need to be programmed. You can program in all kinds of special features like default positioning. Welcome back. Um, uh, you can actually put in a linearizing function if you want. They do draw more power, but the thing that I'm going to count on is you can actually program the deadband to 0, which is to say the thing will continuously hunt. And what this means, if you allow it to, is the servo will just eat itself alive if it operates in that mode for an extended period of time. Number one, it'll overheat. Number two, the gear train will eventually be damaged. For our application here, though, we'll power the thing up, have it slew around, do the things it needs to do, and then sit there and hold. Again, it has exceptionally good powered holding capability, which is very important if you have a huge moving surface on an aircraft or something. Again, not required for our application. And in theory, and this is my next series of tests, will be to say how smoothly, or at all for that matter, can I make small adjustments to bring myself in. And if I am working in a tracking mode, the mirror will be humming. This thing makes quite a lot of noise. If it's making noise, it must be moving. So I just want to see if that shaking of the mirror, however small, would affect the stability of the image. Okay, so, you know, I'm a mechanical engineer by trade, not a software person. So what we're going to have to do ultimately is take a picture, analyze the picture, do a plate solving on the picture. How far am I from my desired spot? Because although we only have to make a small change, with the assembly you'll actually be able to look at a fairly good part of the sky and do a quick, you know, go off, oh, here's this, here's that, blah, blah, blah. What you really have to do is you have to establish the difference between where you want to be and the current orientation of the coordinate system within the device. And again, because these will be relatively small changes, you can use quaternions or Euler angles or something. It should not be a hard thing to do. So again, the digitizer I use is the pen called Dazzle, and it turns out the Dazzle, along with the Hapag and the Easy Cap and all these other things, use the so-called EM28 whatever chip. And what I'm finding is that there are many Windows, even Windows 10 drivers for this chip, but the Linux platforms like the Raspberry Pi, the drivers either don't exist or they're unbelievably flaky, but we will want to be able to capture a single frame. So I have a lot of software work to do on this and a bit of firmware work, and we just heard a number of other capture devices are available that might be used. Next slide. And so to that point, because there are so many cameras and so many digitizers and so many things in use, I'm coming to the conclusion that what I might want to do is, for whatever bit you choose to put into this thing, I will momentarily rotate in a separate standard camera. In other words, I only have to solve this problem once, not 50 times. And so that's, basically between the mirror assembly and the telescope, I'd use another servo presumably to bring a little webcam-like thing in there and use that for the alignment process and then pull it back out of the way. And something that could be important for the future, it's really tempting to design to something that exists now. But when the Gaia catalog is 5 or 6 years away, I kind of like to design this thing to be useful using equipment that's going to be existing and readily available in the future. I mean, our analog cameras are very good, but who's going to be making them 6 years from now? I don't know. So the big thing these days is the Internet of Things, which means you might take this thing out of your car, stick it on the ground, and then pull up your iPad or your iPhone or whatever it is 6 years from now and interact with that. And although I love woodworking, clearly at some point in the future, making all the bits for this, it's going to require, or at least it'll be desirable to use a 3D printer to make the mounts and the little bits. So that's, I've taken on a big project, I realize that. But that's kind of where my thinking is. And again, I have no sky to look at, so I have nothing better to do. So next slide, please. Yes, and so yeah, and I'm certainly willing to correspond with anybody on this thing. There's my email address there. So it's a work in progress. I believe the digital servos will solve my short-term problem, at which point I then have to pull out my programming books, and which I do, but I'm not as comfortable with that. Okay. Yes.
Bill, you finally awakened me from my zombie-like status from all of last night's events. Go back to your very first slide, where you said if you want to get something like this done, ask somebody to do it.
Yeah.
I am the father of 4 children and 20 grandchildren. And this is the thing I would ask either one of the children or one of the 12 grandchildren to do. Because they're all over this stuff.
Yes.
You guys who worked with my son Mark, you and somebody on the website stuff, I wanted to make, and you remember the website when I first got it, David, it was just minuscule and almost nothing. So I asked my son Mark, go to these guys and now we have a great website, right?
Yeah.
Now,
My experience is this is what you have grad students for.
we were doing this, and he said, send my regards to the guys, Steve and whoever's on the other end of this. And he said, well, Daddy, you know what? We just did. Mark is very much an outreach person in physics at Ohio University. Everybody else kind of huddles over their physics, and he goes out and does things. He said, well, they've asked me continually to do things in the community. So what I did, apropos of your list of things, is I put a sensor on my arm that would say that my arm is got an electrical signal, and I could move my middle finger. And across the room, I could make things go backwards and forwards and upside down, and so, based on just pointing at them, okay? Now, that's the kind of thinking that's going on in this population of our world right now. My major telescope is a 14-inch Celestron thing, which fell out of the sky as a piece of junk. But the grandchildren have put Arduinos and all those things you just talked about all over it. It's a rat's nest of things, and it tracks to an arc-second like a dream. So it's really exciting to think about this. I think right now, if I were going to do it, I'd call in the kids and the grandkids.
Oh,
and
very good.
would go for it. It can be done very nicely, I think. Now, the serious tracking that I have was done by S-big cameras. The refraction plate that
Hmm.
does the depth optics.
Oh goodness. Yeah.
That's that's a marvelous piece of two-dimensional tracking, which I don't know.
Yeah.
Anyway,
And
you make
again.
me all excited now.
Oh well, very good.
I don't know what to do, so if I had to do it, I'd ask the kids immediately.
Okay. All right. Any other questions or comments?
How big your field of view is,
Well,
is going to affect how you really address the problem.
yes, and how large a mirror you need, and yeah.
I started thinking about things like this years ago, and I was looking for the widest field of view optic I could possibly buy. And I found a 5-inch aperture f1
Oh,
that was built for the military.
yes.
And if I could match that to a good camera, then you could get a couple of degree field of view, and that really cuts back your requirements here.
Exactly.
Per point.
Yeah.
So the assumptions you make with how large of an aperture and how thin the magnitude you need to go to, you end up with a very different device, one path versus the other.
Yeah, and also it's going to kind of depend as well on kind of where in the sky the thing is. In other words, how this thing would perform when looking nearly vertically is very different from the horizon. That's why I'm kind of excited about the idea of having the tripod with extendable or movable legs. Something to think.
Can you repeat these questions? Nobody on the net is hearing any of this.
Oh, okay. All right.
Just give them Art's comments verbatim, and I'm sort of a summary.
Okay, yes.
Steve said something summary, and then they'll know what we're talking about.
Okay, yes, I'll summarize Art's comments by saying that if you have children and grandchildren, let them do the work for you. Yes. And Steve's comment was basically depending on the width of your aperture and just the geometry of the telescope, the device might require a very different shape or size as appropriate.
I would suggest that you have the telescope pointing down instead of up,
Oh.
and that the mirror be facing the sky, and then you won't have as big a problem with the aperture.
Oh.
If you can use gearing from the farmer peak
Okay, yes, and so Roger suggested that it might be better to have the telescope in effect pointing straight down and then the mirror scanning up into the sky as appropriate. That's actually good.
Again,
Oh.
you got my mind rolling, I may be away past a while. In the 1950s, I was a soldier, and I taught electronics and things like this. I would suggest that for about $1,000, you can buy an obsolete 90mm gun mount, which will do exactly this. If you electronically tell it where it should go, it'll go to the azimuth and elevation to solve the problem. And it's all mechanical.
And it's 10 times my price
And it weighs how many tons?
Oh, it's a little heavy. It's a little heavy, but it is obsolete.
Yes, well, yeah, well, yeah, well,
It's obsolete.
right,
We never went to war. We didn't make a war for them.
right, well, as I pointed out, I looked around at what sort of proper professional devices are available, and everything I've talked about exists at great expense. So my job is to make it cheaper. Or
I understand. Thank
yes.
you.
All right. Thank you. Any other comments? Okay. Thank you.
Thank you, Bill. Very stimulating talk.